think that what Professor Prueba has already done is more than complete. So, well, the title of this talk is non-locality in a 2-qubit system and the PBR theorem on the basic channels. So let's see. This is basically the outline of what I'm going to present today. Of course, at the heart of the talk, it will be the Bell theorem. But in order to arrive to that result, Bell had to introduce first, Bell's theorem is related with the property that is called locality. And in order to talk about locality, it is necessary to introduce first the framework, the general framework that is called ontological models. And we wanted to remark here that not only the Bell theorem allows us to talk about locality, but also, let's say, it leaves the door open to talk about other properties. For instance, here, completeness and scientificity, that in principle, this property is, as you will see, it is related with completeness, as I was saying before. We have the first thing that we've got to do is to define what an ontological model is, and basically these two are two let's say directions that I'm going to address today. So also, of course, from this part, we are going to, let's say, remark the Bell's theorem, but also from using, regarding this scientificity property, let's say a recent result has appeared about that property that actually it is a bit controversial, and we are going to talk about that. That is called the PBR theorem. So let's see. In order to introduce the concept of ontological models, first, let's see in this slide. Essentially, here we have the bond rule from standard quantum theory. So, basically, the idea is from the formalism of open quantum systems. We've got, for instance, here a bipartite quantum state that is represented by a density matrix, and we've got two observables, and the idea is each one of those observables, it is possible to decompose. It is possible to decompose them into the spectral decomposition, and where these values are the eigenvalues of those observables, and these operators from here make a set of measurements, or POVMs, that in principle are like the generalization of projections, standard projections. And then we have that the spectrum.
What is a POVM?
I didn't put it there, but essentially it stands for positive operator valued measurements. It is operators because they are operators, and positive because they are the properties that we want to have for those operators. Okay, so here we have the expected value of those two observables in the quantum state rho, and if we introduce those decompositions here with this, and from the standard interpretation of those expected values as an average, we have that this part here we can understand it as a joint conditional probability function. So we have the system in a quantum state rho, and we choose two measurements, two sets of POVMs, x and y, and the idea is that we want to know, given the quantum state and those two measurements, we want to know the probability to obtain outcome A and outcome B, well, in each one of those parts. That's what I represented here in this picture. And well, this is just that. This is the standard bond rule in quantum theory. But now, as Professor Reina has already commented, and also from the talks of the very beginning of our seminars, Carlos addresses that issue. Professor Roldan also has talked about the APR article and let's say the criticisms towards quantum theory that Einstein, Podolsky, and Rosen made in 1935. And so in order to introduce the concept of an ontological model, let me just redraw this picture from here. We've got here a set of quantum states. We've got ρ, and which we have a pair of measurements, x and y, and we want to know the probability to obtain specific outcomes A and B. So in other words, this probability somehow, well, it is relating quantum states with measurements and outcomes. So now what Bell did introduce in order to somehow formalize those ideas from APR article was the ontological model concept. So basically this part is the same that we had before. And well, basically in the APR article, they wanted to attack quantum theory in the sense of saying that quantum theory is not a complete theory. So in order to, let's say, think about somehow in order to complete the theory, that's why it is necessary to introduce this set here that is called the hidden variable set, where essentially in that set we have all those variables that in principle could help us to complete quantum theory. So if we introduce this set here, the hidden variable set, and now in the same, let's say, in analogy with this interpretation we've got here, it is quite natural to introduce other two joint conditional probability functions that relates, in this case, quantum states with hidden variables, and in this case, hidden variables with measurements. And if we introduce this in this way, with these joint conditional probability functions from a standard probability theory, we have that this probability that in principle we already have from the standard quantum theory, with these three, let's say, this space and these two conditional probability functions form the ontological model. These three objects from here. So if we introduce this like this, we can reproduce these probability functions through something that is well known, that is called the total probability law, that comes from probability theory. So these functions from here, it is possible to reconstruct them using these two functions and of course this space here. So it is like to follow this path from here. So in this way, it is the ontological model concept, and here we regarding these two functions, it is possible to talk about those functions and to impose conditions over them. For instance, the locality condition that Bell introduced is about this function from here, the one that relates hidden variables with measurements. And this function from here is the one that in principle deals with completeness, and as we will see in the next slide, scientific. But in principle, let's be in this way. For instance, completeness, in other words, means that in this case, the probability function that relates states with hidden variables we have like univoc correspondence. We have that given in quantum state, we have a unique, a hidden variable that is represented as quantum states. Or in other words, we don't need something else in addition to quantum states. It is enough to have quantum states. So quantum theory is complete. So in this way, in these ontological models, there's completeness.
Excuse me. Why don't you mention the main argument of the EPR paper regarding completeness and locality? Because now you're going to move to bells, and I would like to have the argument very precisely stated, so we relate it to this Bell theory.
Yes, okay. As I was saying, the EPR article in principle deals with completeness. But here, and that's why I didn't want to put that. I didn't put it here. It is because this formalism came in the work of Bell in 1964 in principle, but the ideas behind the formalism came from the EPR article. So, for instance, here we have in this review where this guy, let's say, formalized that a little bit more. But the issue is that, as far as I have seen, to reproduce the EPR article in this formalism, it is a little bit tricky in the sense that, I've seen that it is kind of a controversy about if Einstein wanted to deal with this completeness that it is defined here, or the scienticity that in principle is a little bit more general, that completeness as we will see. So that's why I didn't put it here explicitly. But in principle, the idea behind EPR article, it is to go against completeness. Put conditions. The idea is to put conditions in these functions such that to find a contradiction, and so we have to discard completeness. So that's in principle the ideas behind EPR article. But as I say, that's why I didn't want to put it here.
But you haven't mentioned locality in the EPR argument. Locality is a very central point, as defined by Einstein also.
Yes, the issue is that in this review, for instance, one way to put EPR article is essentially to assume these two properties, completeness and locality. I repeat, it is just one way to put it because in the original EPR article they don't. Of course they don't use this formalism because it was not there at that time. But so for instance, in this review, one way to let's say try to understand the EPR article is in principle to consider completeness. So we assume that is true, and also locality. We assume those two conditions, and we obtain a contradiction. So that means that some of those two properties must be wrong. So since locality in principle appears to be like a natural property, that's why the EPR article they discarded completeness. So that's why that is one way to put the EPR article. But other people let's say answer to that argument, saying that in principle in the original EPR article they talk about it is about scienticity instead of completeness. So that's why I didn't put it in that way. But in principle it is to go against completeness. So that's what we've got here. As I said, scienticity will see it in the next slide. And now locality, in principle, this joint conditional probability function, it is in principle relating hidden variables with measurements. And so here we have that in terms of this hidden variable, in principle, the measurements over separated parties in principle must be independent in relation with this hidden variable. So we have here what is called a probability independence in terms of probability theory. And well, that is the locality that Prueba introduced in the formalism. And the question is, of course, if it is possible to, using the ontological model framework and these properties to see if it is possible to recover quantum theory. That is in principle the question. So from this point on, I'm going to, let's say, divide the talk into parts. First, I'm going to go through this part to talk about the PBR theorem, and after that, I'm going to show explicit proof, or at least a sketch of the proof of the Bell's theorem's proof, and some things that we have, something that we have already done here and something that we are currently doing with non-locality. So let's begin with this part from here. As I said, completeness, in other words, is that there is a one-to-one relation between states and hidden variables. So in other words, we don't need, in principle, something in addition to quantum states. Now, scienticity in principle is, we can think about it as a generalization of that completeness in some sense. In principle, here we have the relation with
excuse me. I still don't understand this completeness, what that means. Could you explain me a little more? Because I put there in the equation of the integral, what happens? What do you mean by the completeness? Do you mean that if you put the hidden variables, that's all? That you need to state the objective state of the system, or what?
Well, in principle, as I see it, in this case, it is not necessary. It is not necessary to introduce hidden variables, because in other words, there is no need of them, because quantum theory is complete. Here in principle, well, here we are saying that for a quantum state, we've got a hidden variable that is related one-to-one to that state. So, in other words, a quantum state by itself, it is enough.
What is lambda?
Lambda,
hidden variables.
The hidden variables in principle. But now that you comment that, I would like to add something there. It is the fact that, something that I found, personally, I found a little curious, because, for instance, here we've got quantum states, and that those states lie in a very well-known, let's say, mathematical framework. Those are Hilbert spaces. Here we've got operators over Hilbert spaces. But in this case, here the minimal requirement, in principle, this is just a set. The minimal requirement that we want to put over that set is that at least we could define probability functions. That is the set, it is measurable. But in principle, I am not commenting that here, or that is something that I found curious. It seems like there is no structure at all there. And for instance, for these proofs, to prove that some quantum states are local with this definition, I've seen that it is possible to introduce different, let's say, obviously, if you want to make that integral from here and to prove this, we have to introduce I've seen that people introduce different sets, spaces to prove that. So, for instance, regarding the question, what is this lambda principle? It is an element from this set, but that set, in principle, seems like well, it doesn't have a well-defined like mathematical structure. And okay. So as I was saying, let's see first this part. This scienticity property in principle again is a property for those functions mu, and in principle well, of course those functions are conditional joint conditional probability functions, so those are well, in principle are probabilities. So in principle I am representing them here as proportionals just for the sake of the talk. And for instance, for completeness, we've got that those functions are at delta. And now, in scienticity, we can think, we have a set V of quantum states. Let's see, we have two states here, and that in principle we want them to be different for two quantum states. And that set satisfies scienticity if those the two functions that are related to those two states, that are these two ones, have this joint support, where the support is the region where, for instance, the red one, we have that there this function is different, and here this is the 0, and we have that for this red graph, the non-zero region lies on this part, so this is the support of the function. And the support from the green one is this part. So scienticity in principle it is telling us that the support of those two functions are disjoint. These two supports are disjoint. So, and in principle, well, we can see that as a generalization of a delta. In the sense that, of course, if we make those supports just a point, we have a delta. That's why we can think about completeness as a subset. The set, the quantum states that the set of quantum states that, let's say, satisfies completeness are a subset of those that satisfy scienticity. So in that sense, from now on, I'm going to call like scientificalism or scienticity in regard of this property. Okay, so that is the property scienticity for sets of quantum states. And now I'm going to address this that in principle, well, it came out in 2012, and it was kind of, well, I think it is still kind of controversial about these issues. And in principle, it has this title of the reality of the quantum state, and it addresses scienticity. So let's see what the theorem is telling us. Okay, I'm going to let's see first the statement of the theorem. In principle, the statement is that if we have a set P made of quantum states, and we have all quantum states, pure quantum states, if we just consider quantum states, not the general set of mixed states, but quantum state, pure states, and we assume this property that is called preparation independent postulate. I'm going to talk about this in a while. Then, with that definition of scienticity, that set of pure states, that in principle, it is kind of strong, because here I'm not saying, the theorem doesn't say that there is, for a bipartite, it is in principle general. For a multipartite system, for in principle any dimension of the subsystem, we have that set satisfies scienticity. So in these words, in other words, we have that set has that scienticity realism property. So, but again, well, that is in principle the statement, but again, here we have this in principle, this property that actually it is like the focus of all the controversy about that result. And in principle, that property is telling us the following. We have a quantum state that we made of, let's say, subsystems. In principle, that function that is associated with that quantum state, the bigger one, this is the preparation independent postulate. We can write it like they were independent. Like we can, let's say, prepare those states independently. So that's what, that is the condition. As I say, that is the focus of the controversy. And again, well, as you may have seen, assume things in this kind of formalism, in this kind of kind of strong. So well, but that is the result. And for so
is lambda still a hidden variable?
Yes, that is the hidden variables.
And what is mu?
This mu from here, it is the function that is related with this state that is the bigger state. And these mu functions from here, the little ones, are related to these little quantum states. Okay. So well, that is the statement. But in principle, actually there is something I want to comment before I enter to our work. In order to, of course I'm not going to reproduce the proof of that here and here, but I'm going to show some tools that we are going to need to the following thing. In order to prove this result, they have to work with something related. They consider a set of two states, where those two states are this is the expression for a qubit. So we have here x runs from has just two values. We have two states there. Each one of those states it is a qubit, right? So we have two states two states of a qubit. And now if we let's say increase this set of states p, let me call it p n, and then in principle is a set of states of, in this case, this x runs in this way. So we have a set of 2 to the power of n states of n qubit system. Because here we have the density matrix for this state that is an n qubit system. So we have here 1 qubit, and here we have n qubits. In principle, as we saw in the previous slide, we can this scienticity property is defined for sets of quantum states. So they were analyzing the scienticity property for this state, for a qubit and for n qubits. And here is one of a result that we are going to need. Here we have already defined those the set of those states. And we have, as we can see, there is a theta parameter there. And so we can define a function for that takes each one of those states. So it is a function that depends on theta, and also in the amount of qubits that we have. And they work with this system, and I'm not going to show the concept here, but we have that if this sigma function that they were working with it is 0, then we have that those sets satisfy scienticity. It is of course not that general. Here we're talking about qubits, bipartite systems, which each one of those systems is a 2-level system. In this case, here is quite general. Here we have n qubits. So we have this property from here that in principle this sigma function is possible to calculate it numerically. Here, this is still part of the PVR results. We have here this sigma function, and here we have the parameter theta, but in this case we have sin of theta. And again, if we have sigma, the sigma function equals to 0, we have that the system satisfies identity. So, for instance, for 1 qubit, we just have this point. For 2 qubits, we have this region from here, from 2 qubits, and so on. In this case, PVR, these guys could prove this result in both ways, analytically, that are those vertical lines, and numerically, that are this is actually a minimization process. So this is their system, so which runs from 1 qubit to n qubits. And it is kind of interesting because, and I just want to remark as well that in this part, here we have to use preparation-independent postulates, but in this part, talking about just qubits, it is not necessary. So we just didn't want to enter into that discussion there. So. That's what we've got here. It is interesting by itself because we have that 1 qubit, 2 qubits, and while if we increase the size of the system, we have that it is possible to show that this 0 region covers all this region from here. So we have that. With the scalability of the system, we have that, we say, scientific realism appears while we increase the system. Well, that's a bit nice, is what I mean.
What is sigma?
Sigma, it is, well, actually I didn't define it here. It is this function, actually. This function, it is actually this maximum over a set of POVMs. Here we have, let me put them like this, and this is a case. It is actually because we want to achieve sigma equals to 0 in order to prove scientificity. So that's why we have to search for a set of POVMs in order to calculate that. As I said, we made that numerical. But in principle, the interpretation of that property, well, I have to reproduce the theorem to give like a glimpse of the interpretation of that. But in principle, it is that function. So that's what we've got there, and there is the standard. That is the result. And now, there is in principle 1 qubit and n qubit system. So in principle, we can, let's say, ask about what happened with that n qubit system if we make it interact with an environment. In principle, here we have just, this system is made of n qubits, but n qubits in pure states. Those are n qubits in pure states. So what happened with that result? That was our question. If we make it interact with an environment, well, there are different ways to introduce environment. We worked with the easiest ones. For instance, with simple noises, where we tried different configurations. But essentially, for instance, here with 2 qubit system, we have that in principle we lost. Except for this white noise, we lost the 0 region. So let's say we lost the scientific property. But for instance, for n equal to 3, this blue line is the system without noise. So we have that if we introduce the noise, this 0 region gets reduced, but it is not. We still have at least some AC origin part. So well, for n equal to 4, happens something similar. Well, so that is in principle the part of ABR theorem. The system interacting with noise and what happens with cyclicity of that system. Okay, so let me go back to this part. Now that is the locality property. Well, as I said, as I explained before, in principle, this property is like the, it is the meaning of that property that it is the independence of, the probability independence of the measurements regarding the hidden variable. So we have the measurements that occur in the party A, and the party A, it is independent of the part B. So well, let's see what happened there. We have that. Well, here we already have the probability, the locality condition, that in principle that function. We have the locality condition, and again we can translate that to the expected values or the expected values. So we have something like this. And with these two properties, and well, this was actually going to be the original, let's say, focus of my presentation in December. But this part from here, with these two with locality condition, it is possible to derive some inequalities that are called Bell inequalities, such that if we accept locality, the quantum states must satisfy those inequalities. If we switch this implication from here, we have that if a quantum state violates one of those inequalities, that state it is automatically non-local. So that is the way to search for non-locality in quantum states. Let's say it is the most famous inequality that is called the CHSH inequality. In principle, here this inequality holds for 4 observables, and it has this expression where these functions from here are the standard expected values from quantum theory for these 2 observables. And here we have the quantum state. And the locality condition impose this bound of 2 from this expression from here. And what Bell did was, well, of course, in addition to introduce all the formalism, to introduce all the formalism and the property and to derive the principle of this inequality, what was to, in other words, we can understand the Bell theorem as a theorem of existence. To prove that at least the first quantum state that it is non-local. So he used this state for a 2-qubit system, and he introduced those 4 operators in this way, where those are the volumetric matrices, and these are 3-dimensional vectors. And if we introduce each one of those 4 operators in this way, and if we choose these real vectors in this way, following this pattern, and if we introduce everything here, we calculate this function, and again this one, it is possible to show that this function from here achieves this value, that of course, that if we compare it with this bound, of course this is a contradiction. So that means that the condition that we were using to derive this inequality from here doesn't hold for this quantum state. Or in other words, this quantum state is showing non-locality. So this is in principle the Bell theorem. As I said, in addition to the general framework, he showed that this quantum state it is non-local. Of course, course, after that work, we have non-locality. We have that non-locality appears. I mean, this is a 2-qubit system. Non-locality appears in a multipartite system and in each subsystem in more levels, in qubits, and that's in those scenarios. So, well, that is in principle the theorem. Okay, so now I'm just going to, let's say, I mean, there are a lot of things there, but I'm just going to do a review. Of course, we can think about, I mean, now we have non-locality as a property of quantum states, so the natural question is to ask about the relation between this property with other properties of the quantum states, and it's an entanglement. And if the quantum state, for instance, when the issue is that here we have that this quantum state is pure and it is entangled. So what happens if we choose another kind of state, a general mixed state? What happens with that, where people let's say, work on those issues? And in principle, for instance, in relation with the entanglement here, this is just a representation for general quantum states. So this is mixed states in general. Here we have in this part states that are separable, in this part states that are entangled. And we have this part in here that states that are pure. So we have that, well, one of the results here is that non-locality, those states that are non-local must be inside of entanglement, of the entangled set. So in order to have non-locality, we have to have at least entanglement. And we have, for instance, another very nice result that is every pure and entangled state, it is non-local. Well, those are results that people have found. And also that all pure entangled state violates that inequality that I have already shown you. And as Professor Reina talked at the beginning, we have that these ideas have been already, put in the laboratory in the early 80s. An aspect guys proved experimentally that those states actually violate those inequalities. So in principle, here we have that non-locality is a part of nature. Now, for instance, here is another nice thing is that we have that until the late 80s, the only one, let's say, inequality available was the CHSH, but in the late 80s, people began to introduce like a geometrical approach to those inequalities, and well, actually, this was going to be the topic that I was going to present, but okay. For instance, it is a systematic way to generate Bell inequalities. For instance, just to give an example, this is the simplest one, and the next one, let's say in that category, it is this one, and also in the late 80s, people began to understand more about those properties and began to design protocols that use those properties of quantum states, like entanglement, in particular non-locality, for instance, cryptography, just to give a few examples, and composition. And now, from the early 90s, let's say like a sort of a generalization of the concept of non-locality has appeared. That is the superactivation and activation of non-locality. I have already talked about these two properties in previous talks. And now, for instance, a very nice result from 1995 is that, in principle, for instance, but for these CHSH inequalities, we have to find 4 operators such that we maximize this function in order to overcome this bound and to show non-locality, but we have to find those 4 operators. A nice result from the 1995. They found, for a 2-qubit system, like in the case that we were discussing a way to determine if the quantum state if the quantum state violates or not the CH-SH inequality without thinking about to find those operators. So they maximize this function in terms just the quantum state that we are given, that we introduce. So that is then. Well, in principle, I've been studying a bit of these properties, but lately, Professor Reina wanted me to see how to let's say apply those properties for a 2-qubit system, since those are the systems that Professor Reina has been working with. So, in principle, that is what I'm going to present here. So we have, again, this function that we want to maximize in order to overcome that bound imposed from locality. So we have to find those 4 operators, and well, I'm not going to do that, but in principle, let's say the conclusion from this part is that everything relies on the quantum state that we introduce. So at the end, we have a criteria to say if the quantum state of 2 qubits holds or not the CH-SH inequality. So that let's say this algorithm that we got here is the one that in principle you can use for the system that last week Christian was talking about, that is a 2-qubit system. And well, unfortunately, for instance, there is no such maximization of this function for the other inequality. Well, actually, I think it is the only one that I have seen so far. So we are using, well, that is now what we are currently doing. We are using this algorithm to talk about non-locality in a 2-qubit system. And now here I'm just want you to remind last week the Christian's talk. And in principle, he talked about a 2-qubit system that in principle is interacting first when they are interacting together, and well, this is the Hamiltonian part for by themselves. They are interacting together and also with an environment, and so well. One of the things that Christian pointed out last week is that in that specific system, it is possible to design quantum gates. For instance, to create entanglement. For instance, we have that if we begin with this state that is separable, we can achieve this state that is intended, and again, in a periodic way, we have this process, and that is what we have here. This is a separable state. Here we have entanglement information that in principle is a measure of entanglement. So we have that this state is separable. So we have, let's say, at the beginning that they have no entanglement. Then after some time, we have this entangled state with maximum entanglement, and again we have entanglement in a periodic way. So since Professor Reina and Christian were studying the system, and this is the system that they're working now. So they made this. They calculated that there is this CH-SH derivation in the system, and in principle, for instance, in this part where we have that the system is, it has no entanglement, it is separable. We have that, of course, we have the system is the system doesn't violate the CH-SH inequality, but in this part that in principle we have entanglement, it also turns out that the system is non-local. With this graph, we are sure that the system is non-local. So that is in principle, this is just one of the results that, one of the things that Christian and Professor Reina in collaboration, and they are working with that. Well, in principle, well, just
where is this shift in there? And it seems to be shifted.
Well, actually, it is. I mean, it is actually a problem of how we put the graphs. I mean, it is just
Fine.
sorry for that. Okay. Just a final comment is that I'm really curious about any specific thing here. Is that well, I'm not showing this here, but in Christian work, he has some regions in which appears a phenomenon that is called collapse and revival of entanglement. We have he has a part in which there is no entanglement at all, but after some time the entanglement appears again. So it will be, that is what I'm curious right now, it will be kind of nice if in this region where the entanglement appears again, if what happened with non-locality there. Does it appear as well or not? Well, those are the things that Christian and the professor right now are working with that. Well, I suppose that is all that I wanted to share with you.
Thank you. Questions?
Questions I will have to ask them in that case. In the first part of the talk where you mentioned the effects of noise on the PDR theory, you didn't tell us the whole story because those two graphs that are there are specifically for a kind of coupling, which is so-called collective coupling to the qubits. But in the case of independent coupling, we found that this situation doesn't arise, right? So we found two versions of the PDR result, which is, in one of them it is not possible to find the zero regions. In the case of independent coupling, which is, for us was very surprising, we still are thinking about that, and this is the case for collective coupling. So in this case, the regions appear again, the authenticity as claimed by PDR appear, but in the other case, there are no zero regions, regardless of the number of qubits. I mean, we have tested up to 5 qubits. We don't know, maybe higher values, but up to those number of qubits, there is no indication of zero regions. So just to point that out, because this is like follow this basically follows the result, right? But in those situations, we didn't find that. And in the last part, which is something like
you have no interpretation of this.
There are no zero regions. No? And we already claimed that the regions appear, that they don't appear in that case.
And then why in this model appears the zero regions?
Here we're introducing the noise, like a global noise. I mean, you have n qubits, so we're introducing like the noise acting over all the qubits. And in the way that Dr. Coleman is talking, it is each qubit interacting with a noise each.
With a channel, like independent noise.
Independent noise for each qubit.
And in the last part, the results, I mean, we were very curious because since we have been working with all these entanglement characterization in these molecular systems, and this graph that is plotting there, actually the question you're asking is, the answer is there. I mean, there is collapse of entanglement there and a revival of entanglement. And you see what's happening to non-locality in the top graph. The maximal violation, I mean, that goes between 1 and 2. 2 is the maximal possible violation. So in this case, we not only have the violation of Federic inequalities, but with this system we can reproduce the maximal violation of Federic inequality, which is that graph goes up to 2. So yeah, we haven't performed the analysis of entanglement sudden death in terms of non-locality, because you could have, as Andres said, you could have entangled states which are non-local. So, which do not obey non-locality, right? We cannot say that they're local, but they are not in the category of being non-local, even though they are entangled, which is the graph that you showed there in the sort of a sketch. So here, this graph has been done with the action of an external laser, but we also demonstrate that in this molecular system you don't need a laser and you can reproduce this sort of behavior. This Belson locality appears naturally because the system has a natural interaction and gives rise to this. So, I mean, this is just a curiosity. We could speak about quantum gates like Christian did in the previous talk, or we could put in this language of non-locality. In some sense they are equivalent, although of course this involves a more fundamental thing about the quantum theory, but we see both things can be demonstrated in this particular physical system.
This actually looks like a copy-paste flow, right?
Because inequality follows the entanglement measure, so there are some more or less these are,
Yeah, but the funny thing is that it seems to be proportional one to the other.
Can you interpret that the entanglement of locality starts to rise in the second bar, but the non-locality is zero?
No, there is a shift of the flow.
Or is it a shift?
I mean, this is a
mistake of the...
they're not exactly the same. There is a shift in the graph.
Ah, okay.
but this is
It's
artificial.
very little. So instead of talking about photons, which basically all the experiments are being performed with photons, when other people talk about locality, what we're saying is that we could do this in this particular physical setup. All the algorithm that Andres showed there, we can do with this system. I mean, to compute the whole algorithm to test these Bell inequalities. So basically that's the result there. Another way of testing Bell's inequalities.